Okay, now let's look at exponential functions and their derivatives. Let's look at the definition of a natural exponential function to start with. An inverse function of the natural log function f of x is log x is equal to the natural exponential function and given by e to the x. That is, y is e to the x if and only if x is equal to log of y. Now these are inverse functions, so everything we did in the last unit applies. So let's look at solving some exponential functions. What do you do when you have something like this? 7 is equal to e to the x plus 1. Well, we can apply the log to both sides. So let's take the log of 7 equals the natural log of e to the x plus 1. So I wind up with the natural log of 7 is equal to the natural log of e to the x plus 1. Now, I can rearrange this as x plus 1 times the natural log of e, which is just x plus 1. So I get the natural log of 7 is equal to x plus 1. So to solve this for x, I subtract 1 from both sides. So the natural log of 7 minus 1 is equal to x. Now I can put this in my calculator, and I can do it in my head, and I can get x is 0.946 about. Now remember, you always take it to 3 decimal places for the AP test. So what do you do here when you have the natural log of 2x minus 3 is equal to 5? Well, the inverse of e to the exponent is log, and the inverse of log is e. So I'm going to show you a little trick. I always tell my students to raise both sides to the e. All right, so if that is raised to the e and that is raised to the e, then e to the log is just 2x minus 3 is equal to e to the 5th. Add 3 to both sides, so I can get x is e to the 5th plus 3 divided by 2. All right, if I want to solve this exactly, I can get, well, I can get an approximate number of 75.707. You give it a go and stop the tape, do this, and then come back. Now let's look at operations with exponential functions. E to the a times e to the b is e to the a plus b. And e to the a divided by e to the b is equal to e to the a minus b. Now, let's see if I can show this. Let me look at the first one. E to the a times e to the b. Let me find the log of this. All right? I can write this as a natural log of e to the a plus the natural log of e to the b, right? Using the principles we've used before. So this is a natural log of e plus b natural log of e, and those are 1 right there. So this is a plus b. All right, so I have the natural log of e to the a, e to the b is equal to a plus b. Now, I can multiply by 1, and that won't bother you, will it? Okay, it might, but it's not going to bother me. This is the same thing as multiplying this whole thing by the natural log of e. So this is the natural log of e to the a plus b. All right, because natural logs are 1 to 1, this shows me that e to the a, e to the b has to equal e to the a plus b. Kind of cool. Now you can do this one as well, just put in the negative sign and everything falls through. More properties of natural exponential functions. Well, the domain of f of x is e to the x is negative infinity to positive infinity. So we can have positive and negative numbers here, and it goes all the way back and forth to infinity. However, the range is from 0 to infinity. So these answers are always positive. The function is continuous. It's always increasing and 1 to 1. It's also concave up on the entire domain. Now let's look at the limits, and you need to know these. As x goes to negative infinity, e to the x approaches x equals 0. While as x goes to positive infinity, this shoots off unbounded, so we can say the limit is infinite, or actually infinity is not an actual number, but it is unbounded. Now let's look at the derivatives. You're going to love these, okay? After all of the awful derivatives I've shown you, you're going to really like this one. The derivative with respect to x of e to the x is e to the x. Can you remember that one? And the derivative with respect to x of e to the u is equal to e to the u du dx. Now, let's start with e to the x. I know the natural log of e to the x is equal to x. That's kind of the definition. So if I do the derivative with respect to x of the natural log of e to the x is the derivative with respect to x of x. All right, so I have 1 over e to the x times the derivative with respect to x of e to the x is equal to, oh, that's just 1. So the derivative with respect to x of e to the x has to be e to the x. Isn't that cool, folks? All right, let's try these. The derivative with respect to x of e to the minus 2x. All right, let me let u equal 2x minus 1. du is 2 dx, which is just 1. So this derivative is e to the 2x minus 1 times 2. I'm going to write this as 2e to the 2x minus 1. What about this one? In this case, I'm going to let u equal minus 3 over x. So du dx is equal to, minus 3 divided by x squared. All right, so this derivative is equal to u, which is e to the minus 3x times negative 3 over x squared. Now, you know what I lost? I lost a negative sign. You got to help me out here, folks. So this is 3e to the negative 3x divided by x squared. First person in class who tells me that I missed a negative sign on this page right here gets an award. Now, see if you can do this one. Stop the tape, restart it when you're done. Now, sometimes we want to locate extremo. Where is my function, a maximum or a minimum? All right, if I have the function x e to the x, let me find the first derivative. F of x is going to be equal to x e to the x plus e to the x times 1. So this, I can just factor e to the x out of 1 plus x. Now, e to the x is never 0. So where is 1 plus x equals 0? Well, of course, when x equals negative 1. All right. Now, by the first derivative test, I can see that this corresponds to a relative minimum, even without my diagram here. Because if I put in x equals, negative 10, then e to the negative 10 is positive, and 1 minus 10, so this is negative. And then, of course, if I put in 0, f prime evaluated as 0 is 1 times 1, which is positive. So I know this is a minimum. Give this one a go. Stop the tape. Restart it when you're done. Now let's learn about an interesting formula that actually affects your grades far more than you can imagine. That's the standard normal probability. all populations follow, large populations follow this probability function. And it's always centered around the average. Now, suppose I have this function and I want to find its inflection points. Where are my inflection points? Well, the first thing I need to do is find the first derivative. Okay, so the first derivative of x is 1 over the square root of 2 pi times, what is this, negative x over 2 times 2 times e to the minus x squared over 2. I'm going to rewrite that as 1 over the square root of 2 pi. Those 2's cancel. I've got a negative sign, so I've got an x here. E to the minus x squared over 2. All right, straightforward. For inflection, I need the second derivative. So this is 1 over the square root of 2 pi times, let's see, this is negative x times negative x e to the minus x squared over 2 plus, let's see, negative 1 times e to the minus x squared over 2. Okay, let me just solve this down. This is 1 over the square root of 2 pi times. I'm going to factor in e to the negative x squared out because it's just in my way. And what am I left with? I'm left with x squared minus 1. Now, where's the second derivative? 0? Never 0. Never 0. So when is x squared minus 1 equal to 0? Well, of course, when x is plus or minus 1. So we're going to have these inflection points at x equals 1 and x equals negative 1. So do you see how we can apply this to some interesting functions? Okay, give it a go and show those inflection points. Come back. We have one more thing to do before the end of the tape. Now, we're always talking about how this has applications to functions outside of math, of science. And so let's look at some economics. Suppose Y is a number of shares that I trade in millions on the New York Stock Exchange. And say for 12 years, I say it can be modeled this way. Why? I just did. And this function is true when t equals 0 and will go up until t equals 12. All right. Say t equals 0 implies that the year is 1990. All right. At what rate will the shares be traded in the year 1998? You see, going from 1990 to 1998 means my time is going to be 8. Now, I've already got this all set up so that it's in years. So let me find the first derivative. This is going to be 3,663. Did I lose one? Yeah, I lost a 6. Times 0.1902 e to the 0.1902t. All right, so this is the first derivative. Now, evaluating this when t equals 8 tells me y prime at 8 is equal to about a really big number, 0.1902 times 8, and this gives me 933 million shares. That's a lot. Now, see if you can do this one. Stop the video, finish your homework. Have a great evening.